ideas of using lasers to make things very cold. A lot of good ideas coming out of NIST involving both laser cooling of ions, laser cooling of atoms. And these techniques at the time, around 1990, were setting world records in low temperatures, but still weren't cold enough to make a Bose-Einstein condensation. We needed one more idea.
Ready to journey into the extraordinary world of Bose-Einstein Condensate, where ultra-cold temperatures and quantum coherence reign supreme. At the intersection of quantum mechanics and ultra-cold temperatures, a remarkable state of matter emerges, a state where individual particles unite, losing their individuality and morphing into a single quantum entity. This mind-boggling phenomenon is named after the brilliant minds of Satyendra, Nath, Bose, and Albert Einstein. Picture a substance that exhibits quantum coherence, where particles move in perfect harmony, defying the chaotic dance of the macroscopic world. Imagine a matter so fluid, it flows without friction, exhibiting superfluidity. Bose-Einstein condensate is a fascinating state of matter that occurs when a gas of bosonic particles, such as atoms or quasiparticles, is cooled to extremely low temperatures, just a fraction above absolute zero.
At a sufficiently low temperature, the waves of the bosons overlap, and all of them can be described by a single collective quantum wave. This exotic form of matter is called a Bose-Einstein condensate. It was predicted by Albert Einstein and Satyendra Nath Bose nearly 100 years ago.
What makes it truly remarkable is its property of quantum coherence. Imagine billions of particles dancing in perfect unison, as if guided by an invisible conductor. This coherence allows for extraordinary phenomena, like superfluidity, where the condensate flows without any resistance or viscosity. It's as if the particles move in a synchronized rhythm, defying the conventional rules of matter. The discovery has opened up exciting avenues of research, revealing insights into the fundamental nature of matter and quantum behavior. Now, we'll delve into the captivating properties that make this quantum state of matter truly extraordinary. The first property we'll explore is quantum coherence, a mesmerizing characteristic of the condensate. In this state, particles behave in perfect unison, as if guided by an invisible conductor. They occupy the same quantum state, merging into a single entity. This is in violation of Pauli's exclusion principle of bosons occupying separate states, no matter what. This coherence leads to another fascinating property, superfluidity. Superfluids are fluids that flow without any resistance or viscosity. In Bose-Einstein condensates, particles move harmoniously, defying the conventional rules of matter. To unlock these properties, ultra-cold temperatures are essential. The second property stems from the extreme cold. Cooling the gas of particles slows down their motion, enhancing their quantum behavior and facilitating condensate formation. These condensates enable the observation of quantum phenomena on a macroscopic scale. Quantum effects usually confined to the microscopic realm become visible and measurable in these large-scale systems, providing unique insights into the fundamental nature of quantum behavior. Researchers have the ability to manipulate Bose-Einstein condensates, leading us to the next property. Through external fields and interactions, scientists can precisely control the condensate's properties and create novel quantum states. BECs are highly sensitive to external influences. Environmental changes can affect the condensate's coherence and behavior, making them valuable tools for precision measurements and sensing applications. These condensates hold great promise in fields like quantum computing, where their unique properties can be harnessed for information processing. They also enable high-precision measurements, advancements in atomic clocks, atom interferometry, and even gravitational wave detection. Bose's statistical treatment of indistinguishable particles and Einstein's extension paved the way for the prediction of condensation at ultra-low temperatures. But it wasn't until the following decades that experimental breakthroughs started to unfold. The first significant breakthrough came with the development of laser cooling techniques. In the 1970s, visionaries like Steven Chu, Claude Cohen-Tannoudji, and William D. Phillips introduced laser cooling, using precisely tuned laser beams to slow down and cool atoms. This revolutionary technique opened the door to achieving ultra-cold temperatures necessary for the formation of BEC. In 1995, a groundbreaking moment arrived. Eric A. Cornell and Carl E. Wieman, along with their research team at GILA, successfully created the first BEC using ultra-cold rubidium atoms. They employed a combination of laser cooling and evaporative cooling, meticulously lowering the temperature until the atoms coalesced into a single quantum entity. The excitement didn't end there. At around the same time, Wolfgang Ketterle and his group at MIT achieved their own breakthrough by creating a BEC using sodium atoms. They utilized a magnetic trap and forced evaporative cooling to reach the ultra-cold regime necessary for BEC formation. In 1997, Cornell's group at Gila created a BEC using lithium atoms, and Ketterle's team at MIT achieved BEC with potassium atoms. These experiments showcase the versatility of BEC and its applicability beyond a single atomic species, expanding the frontiers of research. The quantum gas microscope, developed by Emanuel Bloch's group at the Max Planck Institute of Quantum Optics, allowed scientists to directly observe and manipulate individual atoms in a BEC. With this breakthrough, researchers gained unprecedented insights into the dynamics and properties of BEC.
At Aalto University, Finland, researchers have created a condensate of so-called surface plasma polaritons. These particles are mixtures of light and electron movement in metal nanorods. Unlike most previous Bose-Einstein condensates, this new condensate is formed at room temperature.
But the exploration didn't stop there. Scientists pushed the boundaries of BEC research by venturing into lower dimensional systems, such as two-dimensional, 2D, and one-dimensional, 1D, setups. In 2004, Marcus Greiner's group at Harvard University achieved a breakthrough by confining atoms in an optical lattice, creating a 2D BEC. This opened up new avenues for studying quantum phenomena and phase transitions in reduced dimensions. Building upon this success, researchers tightly confined atoms using atom chips and magnetic traps, creating 1D BECs. These advancements enabled the exploration of quantum behavior in one dimension, shedding light on new aspects of quantum physics.
The condensate shows coherence over distances that are large compared to the case of individual particles. This is analogous to the overlapping waves in atom condensates.
The journey continued with the exploration of mixed BECs, where different atomic species coexist in a single condensate. This breakthrough allowed scientists to study the interplay between different quantum statistics, spin interactions, and collective phenomena. Furthermore, researchers ventured into the realm of spinor BECs, where the internal spin states of atoms play a crucial role. This line of investigation provided deeper insights into the complex interplay between quantum mechanics, spin dynamics, and the emergence of novel quantum phases. The ability to manipulate and control BECs has been pivotal in unlocking their full potential. Scientists have developed techniques to create and manipulate vortices, solitons, and other topological excitations, simulating phenomena observed in diverse fields like superconductivity and cosmology. Additionally, coherent manipulation of quantum states within BECs has opened doors to applications in quantum information processing and quantum simulation. Scientists can now control the delicate quantum properties, paving the way for advanced quantum technologies. As researchers continue to push the boundaries, they have explored the realm of hybrid systems. By combining BECs with other quantum systems, such as cavity quantum electrodynamics and optomechanical systems, scientists have created novel experimental platforms with enhanced functionalities. These hybrid systems offer exciting possibilities for studying fundamental quantum phenomena, developing new quantum devices, and pushing the limits of our understanding of quantum physics.
The condensate forms in a picosecond, which is 1/trillionth of a second. How is it possible to observe something happening so fast? The key is in the experimental setup. By exciting the molecules only at one end of the array, it is possible to observe the light emitted by the forming condensate at each position in the array. Knowing the speed of the particles, the surface plasma polaritons, the position in the array maps directly into time. This opens a window to the underlying ultrafast dynamics.
But even at such a low temperature, the energy is not absolute zero. It is weird. Vacuum is thought to have absolutely no energy and at the temperatures such as -270 degrees Celsius. But, you can find out what's so weird about that in this video.